Hey, you guys. Sorry it was so long um, in between those two streams. I know I said I would be back, and I am back, but it was a minute because I'm actually really good at getting distracted. But we're back, so let's just get straight into it. So we got 8:49 here. Oh, also I found a pretty cool thing. So obviously there's this LeetCode. The LeetCode premium ones, but there's also a site that kind of assembles it better. Sean Rashad LeetCode plugins. So here, look at this, guys. So I think it's 180 questions or whatever, but you can see all of the companies. Okay, I find it hard to believe that Google is asking. Whatever though. And you can sort by companies for like for example, if you have an Amazon interview, look at all these. Okay. So it seems like everything is tagged Amazon. How many are there? Okay, whatever. Why is it everything Amazon? I bet all of them are Google too. Yeah, look at this. Okay, whatever. Well, anyway, this is something to use. Like Capital One, for example, which I took. I'd say these are decently accurate. Yeah, like decently accurate. And then what else? I've taken a couple. I took TikTok. Let's see, TikTok. Islands. I mean, the video. Alright, well anyway. Yeah, so just something to look at, I guess, but there is no Roblox on there. I don't think, at least. Sean Prasad, LeetCode patterns. Yeah, there's no Roblox. So yeah, let's do 8:49. Daily question? Oh, I don't know. Length of longest array without no escape frequency. Why do I feel like this is slide? Yeah. Okay, this is perfectly easy. Frequency of an element. Do we keep a freaks? Array is called good if each return the longest good subarray. So case 2. So 1, 2, 3. Longest good if an array is less than or equal. So 1 is equal, 2 is equal, 3 is equal, 1 is equal. 2 is equal, 3 is equal, 1 is not equal anymore. So while, yeah, okay. Freaks for, actually we'll hold an L. L equals 0, longest equals 0, for R, num in enumerate, nums. So while, what is our while condition here? While, so basically one will exceed. So basically, if freaks num is greater than k, then we enter a while loop. While freaks for num is greater than k, freaks nums at L minus equal 1 if freaks nums at L is less than or equal to 0, del freaks nums at L and then up here we'll do freaks num equals freaks, oh wait, sorry, freaks dot get num 0 plus 1 up plus equals 1, this seems right, and then here longest equals the max between longest and the length of our window, and we return longest. What does this do? Well, would you look at that? See, that wasn't bad. See, when it comes to sliding windows, I feel pretty okay. But, what is this? But yeah. Yep. Alright. Well, that was a nice easy daily. What was I doing? Oh yeah. What number we're gonna do? See how distracted I get, guys? 8:49. Let's make sure my quality's still good. Okay. What is up with add two numbers? Why haven't I done this one? It's a linked list giving two non-empty linked lists representing non-negative integers. The digits are stored in reverse. Each of the nodes contains a single digit. See, wait, here's something we can do. If you see add two numbers, you can search add two. Look. Oh, look. See, people are asking, so it makes us feel good. Is anybody at Jane Street? Please. No way Jane Street asked that. Am I right, guys? Alright, so it's in reverse. So basically 2 and 5 adds to 7. 4 and 6. Add the 2 and return the sum is like 4 and 6 adds to 0, so you carry it over to the next one. Okay, so we'll hold a remainder. Remainder equals 0, or remain is 0, and then, are they the same length? I'm guessing not, yeah. While L1 or L2? L1, oh. So like this would be 998. 9989. 9989. 9989. Wait, what? Oh, I'm going 9, 9, 8, 9. 9, 9, 8, 9. Wait, 9. So this is 9, 9, 8, carry the 1. 9, 9, 8, 9. 9, 9, 8, 9, carry the 1. 9, 9, 8, 9, carry the 1. 10, carry the 1, carry the 1, carry the 1. Oh, I see. So while, I think it's L1 or L2, we'll make a new head equals node. And then we'll set cur equals head. So you can we could build a node. Okay, so we'll say new equals node where the val is equal to, the val would be equal to L1 dot val plus, oh actually here, we'll do that math here. Code is L1 dot val plus L2 dot val. So for example, if it's 9, that would give us 18. So divided by 10, round down, is 1. And then you'll add the mod. So to add versus rem plus equals this divided by, divided by 10, which, and then to add equals this with mod 10. Okay, and so new node, oh wait, but we shouldn't add the remainder yet, should we? The remainder goes after. So this is what goes, this goes in here. We'll do to add. And then you have to go after we build the node. Plus remain. Yeah, I like rem better. Okay, and then cur.next equals new. Cur equals cur.next. And then, wait, if it's just L2, it's gonna call it L1.val. If see, this is tricky once you run out, because once you run out you have a remainder, and then you still have the L1. What if this was 4, 5, 6, 7? What if this was like 4 and 6, and you'd have to... So I guess we'll L1 and L2. So this will go to the end, and then we'll have one of the lists maybe. So So you're carrying the 1 and it's going all the way over. How would you do this? I guess while L1 and L2. Is this easy? Oh, it's medium. So this will get us to there, but then if L1 or L2, okay. If L1 or L2, while L1, I guess this will handle that, while L1 or L2, then L1.val, you can't call. Okay, here we'll do if L1 what am I doing? L2. And then while left, left out val. Oh, sorry. Oh wait. Oh wait. Oh, we need to be adding the remainder. Cause like, for example, if this is to add 5, 7. What if this was 5 and 7? Do 2 add plus rem. Not 10. Okay. Left val plus rem. Not 10. To add cur dot next equals oh, sorry. Wait, rem plus. I mean, I guess. Cur dot next equals new cur equals cur dot next. So now, and then if there's still a remainder, we'll just do cur dot next equals a node with the value of the remainder, and then we'll return head dot next. Does this work? What is this? I don't have too much faith in this, to be honest with you guys, but it makes sense to me. Node is not defined. What do you mean node is not? Oh, it's the list node. Oh my gosh. List node. List node. List node. Memory limit exceeded. That's a new one. Well, L1 and L2. L1 equals L1 dot next. L2 equals L2 dot next. That is a big mistake. Left equals left on next. I see. If L2 oh, so there was no L1 or L2. Oh wait, can't I just do if L1 or L2 left equals L1 or L2 else left equals none? Why am I adding? See, look at all the bugs in my code. I mean, this is just horrendous. 7081 0 8902569. What? What? Okay, wait. Here I want to print f to add equals to add and remainder equals rem. So this is for the main loop. To add sub. Okay, wait. Ignore that. Let's go here. To add 8. Remainder is 1. To add 9. Oh. Oh, equals. Oh, wait, it's not plus equal. What is it? Remainder plus? That's plus equals. Wait. Remainder. Oh, it's already in. It's already factored in. To add a. What is this? 8090 124. Let's come down here. To add. Notice how, guys, by the way, I just realized I'm completely distracted again. We were supposed to do 849 and I just saw number 2. But whatever. To add 9, remainder is 1. Okay. To add 0. The remainder is not 1. I mean, the remainder is not 2. The remainder is 1. Because 9 add 1 is 10. 9 and the remainder of 1 is 10. On 10, you're going to add 0. 9, the remainder is 1. What? Oh, this is also. See, like, what am I doing? There we go. Let's comment out these prints. See if this works. Alright. Seems like there's a better way. Okay. What is Jinwei? Jinwei. What is Jinwei? Gold and grape. There we go, bro. Okay, what did everybody else do? Whoa. If H1 is none or H2, while H1 is not equal to none or H2 is, H1 is none. Yeah, this is just a lot. I feel like this makes sense. I guess. Well, I guess that's because I wrote it. But look at us. We have 1, 2, and 3 done. Okay, what was I actually going to do? 849. Excuse me. You are given an array representing a row of seats where seats I equals 1 represents a person sitting in that seat, and seats I equals 0 represents it's empty. There is at least one empty seat and at least one person sitting. Alex wants to sit in the seat such that the distance between him and the closest person is maximized. Okay. I'm getting a 2-pointer vibe. Let me think for a second though. Well, at least one person. Well, instead of looking for people, if we just look for the biggest streak of zeros, that'll work. Is this another sliding window, bro? It doesn't say. Guys, I feel like I'm a bit overdone on the sliding windows. I mean, I know there's never too much of a good thing. Which, I don't know if that's, now that I think about it, I think that's a sarcastic saying. But if it is a sarcastic saying, then I think we're seeing it too much of a good thing. But not in that sense, but more so in the sense that, like, I need to practice other things. Let's test my theory, counting the most zeros. So here, the most zeros is this. It's just 3. So the answer is, what, 3 divided by 2 floored, which is 1. What about here? 3 divided by 2 floored, which is 1. Except it's a border. Two. Oh, I see. Oh, that's how we're counting it. Alright. So if it's at the end, those are edge cases though, right? This is a weekly contest. One of the first weekly contests. Alright. I mean, let's try my sliding window. I think you could slide it. If it's on the edge though, how would you know? Oh, because if R equals, okay. Alright, so it would be while, I guess you could do while sum, but is that the best way to do it? Because sum is O of n. Oh wait, if R is a 1, if R is a 1, you can't sliding window this, because if you hit a 1 with your right pointer, you can't shrink left. Okay, wait, let me think here. Hmm. This isn't that bad. 2 pointers. You could go like Bing, L, I guess you could sliding one L equals. So here, Elmhurst? Okay. Sorry, I'm distracted now. So basically, if we'll set left to basically if C equals 1, we're gonna put L equals R, because we'll reset. So let's get a better test case up here. I like 1. Actually, we'll do 0, 0, 0, 1, 1, 1, 0, 0, 1, or 0, 0, 1. Alright, so L equals 0. If L equals 0, if L, okay, we'll handle that in a sec. Let's think about here. So we get here. As soon as you get here, oh, first let's compute the longest. If seats at L equals 0, then that means we have, so we'll make the longest. So normally we would make the longest max between the longest and R minus L. Not the plus 1 because we're on a seat. But there's a case in which if L is 0, seats at L is 0, if L equals 0, then longest equals the max. Or sorry, you don't have to. Well, yeah, fine, we'll do max between longest, and it would be like, for example, here the answer is 1, 2, 3. Oh, here the answer would be 1, 2, 3, 4. Oh, so here it's R minus L, but here it's gonna be R, like, it's R minus, what? R minus L, if it's even, it has to pick 1. Wait. Wait, let me think here. If it's like this, and there's ones on both sides, it's 3 divided by 2 is 1.5. Sealed, which is 2. Here it's 4 divided by 2 is 2. Sealed is 2. Okay. R minus L over 2 and sealed is. Okay, I like that. And then there's another case where we reach the end. And that case for R. Okay, wait, I guess if R equals len of seats minus 1, Wait, if C equal 1, L... Wait a minute. We leave him on a 1. So it's R minus L. Because R is on a 1. L is on a 1. So it's R minus L. Normally it's R minus L plus 1. But now it's R minus L minus 1. And then here we go, minus 1. If R equals the length of C, if R is the last one, and R, oh, and C said R is 0. Longest, we'll do it again. Longest equals the max between longest and, what is it? It would be, well, like, for example, if we had this, it would be R minus L plus 1, but minus 1, so R minus L. Wait, what? No, this is wrong. Is it just R minus L? Because here it's R minus, here it's R minus L plus 1. It is really minus 1. Wait, here it's R minus L plus 1. But it's really just R minus L. Okay, right. Here's gonna be like R minus L plus 1, but it's really R minus L minus 1. Yeah, so this is R minus L. R minus L. And then just return longest. I suppose. So we got the edge cases down at least. What is happening here? So L is here, R is here. For R, if C equals 1. Okay, so now C to 0, C to 0, C to 0. If C equals 1. Why am I checking if this is not something we need to check? Here we have U here, we have U hit here. So if C equals 1. If L equals 0. And C's at 0. Okay, so if C equals 1, longest is the max between the CO between R minus L minus 1 over 2. So this is R minus L plus 1. So minus 1 is U is 3. Over 2 is 1.5. Why is the answer not 2? Because you divide before you. There we go, this should work. Okay, let's submit that. Let's see if that works. Okay, it works. Very cool, very cool. Thank you, test case. Exam room, task scheduler 2. What did everybody else do? What? If seats is 0, 0, or seats are negative 1, seats. Max between the seats dot index of. Oh, that's smart. That's smart. That's smart. And then for I in the range from 1 to length of seats. If seats at I is 0, up the count. If it's 1, max is the max 0 is the max, and count 0, 0, max this is max this, max 0. Over 1, over 2, floor. I like that. What'd y'all do? Okay. Okay. Let's see. What else do we have? Summary sums equals. Oh wait, I should write this down. Maximize distance to closest person. Was a medium? Yeah. Maximize. This is Roblox. Person. What do I call that? Oh, actually I solved it without cheating, so I call that a green. 1 second, you guys. Let me use the restroom. Una segunda. Alright, I'm back. Let's see what we got next. Oh yeah, so I've done that. Single threaded CPU 1834. 1834. Why does it put me on the editorial? I don't get that. You're given n-tests from 0 to 2D integer NQ time, processing time. It'll be available to process at that time, and it will take that time to finish. With a single threaded CPU, I can take at most 1 task at a time. act in the following way. If it's idle and there are no available, it remains idle. If the CPU is idle and there are available tasks, the CPU will choose the one with the shortest processing time. If multiple tasks have the same shortest processing time, if multiple tasks have the same shortest processing time, it will choose the task with the smallest index. Okay, so whichever comes first in my right. Once a task is started, the CPU will process the entire task without stopping. Once the task is started, the CPU will process the entire task without stopping. The CPU can finish a task and start a new one instantly. Okay. So return the order in which the CPU will process the tasks. Okay. So this is available at time 1. So these come sorted, but are they... I don't think they're necessary. 7777. I don't think they come sorted necessarily. So I'll sort those. See, I have a question. Please tell me the time complexity result for each code complexity EX a 10 to the power for input. For example, the answer for n is 10 to the power 4, and n squared is 10 to the power 8. But I also want to know for everything else, like n log n, log n. Because I don't know n of 1 for 10 to the 4. Log n 13? Holy. N log n is up. Don't ever give it. Don't return answers to me in scientific notation. One, 10 to the 1. So log n is 10 to the 1. Square root n is 10 to the 2. Well, that makes sense. N is 10 to the 5. It said that? Half down n. Who's doing what is n factorial? That's like n times. Oh my gosh, I don't even know. And log n's 10 to the 5. And where is 10 to the 8? If I have a 10 to the 8 input, is n log n possible or no? See, I'm asking the questions that matter, guys. This is why you gotta tune in. Oh, no, you gotta add 1 for n log n. Yeah, that's generally too slow. Yeah. Yep. Because Binary search is just log in. Just 10 to the 1. Holy. Wow. Wow. Oh, anyway. Where were we? So we can definitely sort this. So sorting it, we'd have 1, 2, 3. We'd have it like they give us. So it starts at 1, it takes 2. So for all the ones that start at 1, how do you determine? For all the ones that start at 7, go. Yeah, we get that part, bro. You could do a priority queue. Is this a priority queue problem? Yeah, it says it is. Okay, well first let's sort it. So tasks.sort key is lambda x, where x the first number. Oh, and then I want the second number. So in the second result, this should give us 727475. Oh. They could even have the same. They could even have the same index. Wait a minute. I can't lose the index. Let's see. So if I priority queue, I mean, like, what even happens if I do that? Oh my gosh. No, don't do it. Oh no, don't do it again. Gosh, I suck. And I was gonna say running too soon. Still running too soon. Okay, there we go. Oh. One, two, two, 4, 3, 2, 4, 1. 7, 2, oh. Oh. Task. How do I do task? Oh, task dot append. Ooh, wait a minute. Enumerate. And I. PQ. Wait a minute, is it this simple? Greater than enumerate tasks push to PQ. Okay, let's make this simpler. For I task in enumerate tasks, task dot append the index, and then heap q dot heap push the task. Heap push got. I keep forgetting. Like, you would think, I don't know why, but in Python, like, everything is so like straightforward and simple. But we have like this whole heap queue thing is not. It feels like another language, like where you're passing in like. I don't know. I'm explaining it poorly. So 43201. 43201. 0123. Ooh. Ooh, wait. After you get to the first one, you start with the second one. 012. What? Because at 1, you're at 3. Hmm. I guess I gotta rethink. Of course it's not that easy. Alright, let me see. So, let me check the semicolon. Whoa. This is medium, okay. So we could hold an interval, and then when you finish a task, like, so 1 plus 2 is 3, and then you could do like while heat pop, and the thing is, yeah, while heat at 0 is less, or is, while heat 0 is, okay. Available is that, and then we can do while PQ I guess if not interval, then okay, wait. Okay, wait. You can do while PQ at 0 start time is less than or equal to our current time, our interval. You can available dot append heat PQ heat pop PQ. Okay, and then so like that would append 1, 2. Now, so that puts all of the ones. Okay. If available, so if any are available, if any are available, so we have like 1, 2. But in this scenario, do we have 2 priority queues? So, oh wait, you don't have to. Oh, we can remove, the time they start doesn't matter anymore. And heat cop PQ, what is this? From 1 on. Okay, so this will append the time and index. Now, if available, if we have some available, should this be another queue? It might need to be another queue. Because this queue would have the shortest times at the front. Yeah. Yeah. So I think you need to do heap queue dot heap push. To available this, and then if available, if available, what is it? Time and index equals heap queue dot heap top available, and then answer dot append the index and interval equal the time, else if there's none available, interval plus equal 1. I like that. And then we'll return answer. Should've just, oh my gosh, what is that? Available. Index out of range. While PQ0. What do you mean? What? Oh, he push. Because we're popping while PQ and 0, 2, 3, 1. Whoa. Oh, because they're all unavailable, so then while available, okay, while available, time index equals heap queue dot heap hop from available. I'll just pop it. Actually, you don't need to add the time. Okay, that works. Okay, so we had a time limit exception. What is wrong with this? What? Time limit exceeded 1 million? Or like, that's more than 1 million, but regardless. It's just too... Okay, task.append. I. While PQ. Oh. because it's going plus equals 1 if it's really big. But why is that such a time limit issue? Wait, let me check the size. 10 to the 9. AHRS8. Oh, so this TLE interval plus. Oh, well. Oh, it doesn't matter. So here's what I'm gonna do, guys. I'm gonna just shoot the interval to the PQ. Interval equals PQ. At 0, at 0. Does this work? Does this work? Oh my god. Oh my gosh. Submit. Because it doesn't even matter. It's not like an interval problem. Oh, okay, 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 okay. So I wrote the most inefficient solution ever. Whoa. Whoa, 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 whoa. While I is not ready, he push ready duration task. Wow. Wow. How did I write such a bad solution? I mean, it was a solution. See, like, is this, like, does this count as a passable solution? Here's what we'll do. Compare the time complexity and space complexities of the following two solutions, and if they're passable. Solution 1, solution 2. And now we'll give it whatever these guys are up to. Oh, you can just copy. Both are O of log n, so both are absolute. Solution 2 is cleaner. A heap insertion is log n. Yeah, I see. Alright, what is this called? Single threaded CPU. which is a medium. Single threaded CPU. I mean, technically I solved it. So I'm gonna have to give it, even though it could have been cleaner. I mean, yeah. What else do we got? What time are we at? Hour 30. Merge intervals I've done. Subarray product less than K. I don't think I've done that. 713. Are these all sliding window? Like, is this a section? Like, what is going on? This is all... Oh, actually, the other one wasn't sliding. Okay, wait, I'm actually... I don't know what I'm doing. Please, given an array of integer nums and integer k, return the number of contiguous subarrays where the product of all the elements in the subarray is strictly less than k. 10 times 5 times 2. Oh my goodness, wait. Oh, this is the at most. Seems like the at most, because you have to count the number of subarrays. Give me a quick sec. Takes in okay. Wait, here's the thing. Here's the thing. So with Atmos K, sorry, I'm on my phone a little, so that's I'm not thinking this whole time. But with Atmos K, it's like Atmos minus the one before it, so it's Atmos 99. Atmos 100 minus that. Oh wait, at least is what we should do. Wait, so it's at least 100, right? 1 second. I'm doing something on my phone. We were talking during the semester. Okay, so I feel like my thinking's wrong. Product less than 100. Because what was the other one I used this for? It was like a sum. What was it? It was like a sum. Oh, it was the exact number that summed to a number. So if you did the ones that sum to at most the number right below, and then subtract that from the number of the ones that sum to that, you get the exact number. But here, if you do products, here it's less than, so it could be a bunch. So what is this like? You can't do sliding window because that doesn't take. Wait. Okay, wait. If two numbers product is it, then each one's product is it. So if you extend and it still works. So like 10 plus 1. Oh wait, no, 10, 5. That gives you a total of 3. 2 doesn't work. But then 2, 6, that gives you 3. So that gives 6 total. Oh wait, 10, 5, 2. What is it? If it's 2, it's 3, because 2. What is the topics here? Binary search sliding window. I mean, I can think of the sliding window where you like being. What does this say this is? Sliding window. Number of the product of all. So like left. Okay, so 10. Extend. 5. So 1. Now we have 2. Extend. Doesn't work. Okay, extend doesn't work. So you do the length of this. How do you get like two distinct turns into... Wait, let me ask. How do you calculate what the number of elements like, what is it, permutation? One, two, three, four. Okay, but how to quickly calculate that in Python? Do I actually have to do some function? Oh, factorial. This is factorial. What? I was just thinking about it's not factorial. 3 times 2 times, but 2 times 1. That doesn't work. Sorry, you guys. We don't need the longest. These all positive. Okay. Alright. I feel like I could definitely... Oops. Where was I? Oh, yeah. Why do I keep typing curpod? Oh my gosh, this is curpod too. What are these cases? Can I get the OG test case? 10, 5, 2, 6, 100. Does it at least work on that? 22. I thought... So if you're there, 22, but it was 8. How did I possibly? I found something wrong. What is... Okay, that's what I thought. O plus equals 1. Oh, because we can only do this when we've exceeded R minus L plus 1. No, or less than it. Oh, because... Okay. Wait. So if curve prod is greater than or equal to K, while curve prod is greater than or equal to K. Let's try that. Here we go, bro. Curve pod. Okay, what did this do? 5, 8. Well, it's because R minus L. Okay, for curve prod times equals 9. So we're at 10. Okay, curve prod times equals 9. We're at 50. Curve prod times equals 9. We're at 100. So it's greater than or equal. Total plus equals R minus L. So 2 to the power 2. Which is 4. Oh, this is minus 1. Wait, but that doesn't help. 2 to the power 2. R minus L, so 2 to the power 2 is 4 minus 1. That's 3. Okay. 10. It's 50. 2. Oh, wait, if curve prod total plus equals what R minus L plus 1 times 2 minus 1. Really? What? Times 2. Minus 1. 5 to 10, 60. So 3, 9, 3, 9. 9, 8. Oh, because there's overlap. Okay, I honestly don't even know what I'm meant to do. Sliding window, Python. Look at this dude. When you shrink the window block to the passengers, the initial set left and right is product of 1, count to 0, right hasn't reached the end. Look, chain that multiply by the current number shrinking window while the product is greater than equal to divide the product by the left nose number below the shrinks window counts 1 plus right minus left plus 1 to count 1. Single element, yeah, right. Increment. Really, bro? Are you serious? Why does that do that? Because here we had 1 and we had 2. 1. Then we had 2. Then we had 2. One, and 2, 2, and 3. Okay. What is this? Separate product lesson K. I already gave my rationale for why I marked this as being done the 11th. If any of you astute people know that it is the 12th, because my reasoning is that I haven't gone to sleep yet or whatever. Alright. Alright, I think with that, I'll probably call it a day. I need to do word search again, to be honest, because that one did not go well, I remember. But I do, yeah, okay. I don't want to do this one. I don't know why this is a hard. I mean, I guess I do get it, but yeah, that is kind of tricky. Alright. Well, what time are we at? 2:19. Alright, well, sorry there was a lot of time that I was on my phone there, but I will see you guys tomorrow.